Hi there. This particular video reviews the idea of information gain, and information gain is a very important concept because it is the basis for decision tree algorithms. And when the algorithm constructs a decision tree or segments, a population based on a decision tree, the basis for constructing the algorithm is this idea of information gain. That's why information gain is an important concept, and the material here is from chapter 3 of the Provost and Fawcett book. Information gain is constructed from the idea of entropy. So we first need to understand the idea of entropy before we can construct information gain. So let's take a look at what the idea of entropy is. So if you have a population that is divided into k classes, class 1 has probability p1, class 2 has probability p2, and so on. The notion of entropy is, or the formula for entropy is p1 times log p1 plus p2 times log p2, and so on. The logarithm is taken to base 2 generally, and this formula is a little bit abstract and may not immediately convey the intuition behind entropy. But entropy, you can think of it as a measure of the purity of a set, and again this is easily illustrated through a very nice picture like so. So in this picture you can see that there are basically 1, 2, 3, 4, 5, 6 different groupings of pluses and minuses, and you can think of the pluses and minuses as, let's say, customers. Let's say the pluses represent customers that are an excellent credit card risk, and the negatives represent customers that are not such a good credit risk. And entropy generally varies from 0 to 1. And it's a measure of the purity of a set. So let's, using the formula that we just saw, p1 times log p1 plus p2 times log p2, if you use that formula to compute the entropy for each set, let's first compute the entropy for this set over here, which is a relatively pure set. It's got 10 negative customers, right? So the probability of a negative is 10 over 10, so the probability of a negative is 100%, and the probability of a positive is 0 over 10, it's 0. So the entropy for this particular set here is, entropy has, the formula has a negative sign in front. Probability of negative is 1 times log of 1, plus the probability of a positive is 0 times log of 0. And again, you may need a little refresher on how logarithms are computed, but the log of 1 to any base, whether it's 2 or 3 or natural logarithm e, log of 1 is always 0, and the log of 0 is negative infinity, and so it's 1 times 0, and so essentially the entropy computes to 0 for this set. I'm not going to compute the if you compute the entropy for I'm going to have to adjust this a little bit. Give me just a second. If you compute the entropy for this set, which contains 5 pluses and 5 minuses. So in some sense, that's a customer segment that's kind of chaotic from a credit card marketer's perspective, because it's got 5 good customers and 5 bad customers. It's not clear that you want to solicit that particular set. But right now we are trying to understand the formula for entropy. So if you look at this particular set with 5 pluses and 5 minuses, you could compute the entropy for that set like so. So the probability of a plus is 5 over 10, and the probability of a negative is likewise half, and the entropy is negative of half times log of half plus half times log of half, and log of half to the base 2 is simply -1. And so you have negative of negative minus half that computes as +1. Similarly, if you go ahead and compute the entropy for this set, which has 10 pluses, you should come back with the same entropy of 0. So intuitively again, or to summarize, entropy is the measure of the purity of a set. And you can see in this picture, it's a nice picture that shows the entropy varying from 0 all the way up to 1, back down to 0. And the entropy reaches a maximum of 1 when you have 5 pluses and 5 minuses. And it becomes a 0 when you have 10 negatives or when you have 10 pluses. So again, to summarize, entropy is the measure of a purity of a set. So what is information gain? Information gain builds upon this notion of entropy. And when you have a decision tree, you have a parent node and you have children nodes. And the information gain of the branch of the tree is calculated as the entropy of the parent, take away the entropy of the children multiplied by the probability of that child class. Entropy of class 2 multiplied by, or branch 2 multiplied by the probability of branch 2. So again, this formula is a little bit abstract, but it will become clear in a second when you look at the picture and follow through with the calculation. So here is again an example, and you can think of these as customers. The customers are either blue dots or yellow stars, and this is the parent node of the decision tree. And at the parent node of the decision tree, we have 16 blue dots and 14 yellow stars. And therefore, the probability of a blue dot is 16 over 30, about 0.53. And the probability of a yellow star is 14 over 30, about 0.47. And so you can compute the entropy of the parent node and the entropy of the child node based upon the formula that we just reviewed. And we are breaking these customers, or the decision tree is breaking these customers into two branches based upon a rule that says, does the customer have a balance less than 50,000, or does the customer have a balance bigger than or equal to 50,000? So that's the rule. And so does this kind of, dividing the customer into two groups, does this rule make sense? How do we decide that? We decide that based upon the notion of information gain. So we first compute the entropy for each of the children. So this is what you would call the left child, because the branch is going to the left. And the left child is relatively pure. It's got 12 blue dots and 1 yellow star. And the probability of a blue dot for the left child is 12 over 13.92. And the probability of a yellow star, is 1 over 13. It's 0.08. Likewise, if you go to the right child is the node with a balance bigger than or equal to 50,000. The right child has 4 blue dots and 13 yellow stars. And we could compute the probability of a blue dot as 4 over 17, 0.24, and the probability of a yellow star as 13 over 17, or 0.76. So to compute the information gain for this kind of branching in the decision tree, we could put it all together using the formula for entropy like so. So let's first take a look at the parent. The parent node, this is the parent node again. The parent node has 30 customers altogether. Probability of a blue dot is 16 over 30. Probability of a yellow dot is 14 over 30. And you can put the 0.53 and 0.47 together using the entropy formula like so. Negative of the probability of a blue dot multiplied by the log of the probability of the blue dot, plus the probability of a yellow star multiplied by the log of the probability of the yellow star. This is a yellow star, so forgive me for my drawing here. And so if you use the formula, you already know the probabilities. Negative 0.53 into this negative 0.9 is the log of 0.53 to the base 2. And this negative 1.1 is the log of this 0.47 to the base 2. So you can compute, the entropy of the parent node is 0.99. And again, I want to remind you that entropy is a number that varies between 0 and 1. And so the parent node is relatively has a very high degree of impurity. Likewise, if you go to the right child, and the right child has 17 customers, 4 blue dots and 13 yellow dots, you could, and the probability for blue dot is 0.24, the probability for yellow star is 0.76, the entropy of the right child is 0.79. You can do the same thing for the left child. You can compute the entropy of the left child. Let me just show you the entropy of the left child right there. The entropy of the left child is going to be negative of 0.92 times negative 0.12. That's the probability log of 0.92, plus 0.08 times negative 3.7. That's the log of 0.08 to the base 2. And so the entropy of the left child turns out to be 0.39. So to summarize, you have a parent node with an entropy of 0.99, you have a left child with an entropy of 0.39, and you have a right child with an entropy of 0.79, and we're going to put everything together to compute the entropy information gain for this kind of a branching rule, which says, let me divide customers based on balance less than 50,000 or balance bigger than or equal to 50,000. So the information gain, again to remind you, is the entropy of the parent node minus probability of balance less than 50K multiplied by the E stands for entropy here, entropy of the group balance less than 50K, plus probability of balance bigger than or equal to 50K multiplied by the entropy of the group that has balance bigger than or equal to 50K. And so that's 0.99 minus of 0.43 times 0.39 plus 0.57 times 0.79. So where did this number 0.43 come from? That's the probability balance less than 50K. So the 0.43 is the same as 13 over 30. So if you remember, there are 30 customers overall. 13 customers fall into the left branch and 17 customers fall into the right branch. And so the 13 over 30 is the 0.43 and 17 over 30 is the 0.57. 13 over 30 represents the probability that the parent node has balance less than or equal to 50K, and 17 over 30 represents the probability that the parent node has balance bigger than or equal to 50,000. So the information gain for the rule balance less than 50K or balance bigger than or equal to 50K is quite large, about 0.37. So here is another example of another kind of branching. You can branch or divide the 30 customers into whether they own their residence, whether they rent their house, or the residence is some other type. And you can again, compute the probability of blue dot and yellow star for each of the. So in this case, instead of 2 children, the parent node has 3 children, 1, 2, and 3 children. And each, the constituent group mixture for each of the 3 children is different. And this picture shows the probability of blue dot and yellow star for child 2, probability of blue dot and yellow star for child 3. I want you to verify the information gain for this kind of branching, and you should come back with these numbers. Entropy of the parent is 0.99, the entropy of the parent doesn't change, but the entropy for own is 0.54, rent is 0.97, and other is 0.98. And so the information gain for this kind of branching is only 0.13. So you can see that the information gain for this rule is only 0.13, but the information gain for this rule is 0.37. So because 0.37 is bigger than 0.13, the decision tree would actually prefer to branch first based on the balance rather than whether the customer owns their residence or not. And that's how decision trees are constructed. You first branch on the rule that gives you the biggest information gain. Then you pretend your universe is just the customers with the balance less than 50K. Then find another rule that gives the biggest information gain for subdividing this group into further clusters if needed, and so on, to construct the entire decision tree. So to summarize, information gain is the concept reviewed in this lecture, and information gain is the basis for constructing decision trees. And information gain